Hello friends, today we are going to discuss the next topic, that is Myhill-Nerode Theorem. This theorem is also known as table filling method. Okay, so first we discuss some theoretical concept and the algorithm for this theorem, and then we take example to solve this problem. So the main important point is that it is an important characterization of regular language, and it also has many practical implications. So this theorem basically used for regular languages, and also that this theorem provides an algorithm for minimizing DFA, which is a vital step in automata theory. As we know that there is another method for minimizing DFA. That method is called partitioning method. We already discussed. In this method and partitioning method, both methods are used for minimizing DFA, but the main difference is that this Myhill-Nerode theorem or table filling method is used for that DFA which have more than one final state. Okay, so this theorem is basically used for minimizing DFA which contain more than one final state. And there is another method which is called partitioning method, in which we minimize a DFA which contain a single final state. Okay, so there are some steps for this theorem, that is table filling methods. So the algorithm say first step is that we draw a table for all pair of states Qi and Qj that not necessarily connected directly, and initially we unmark all. While drawing this table, we create n by n matrix, and in this step itself we delete the diagonal upper part. Okay, the second step is that we consider every state pair Qi Qj, this same pair, in the DFA and find out whether Qi belongs to the F is final state. So Qi belongs to F and Qj does not belongs to F. So one of the state Qi or Qj, one state belong to a final state and other state does not belong to a final state. If this is so, then we mark that state or we mark that pair. After this, we repeat this step until we cannot mark any more states. And if there is an unmarked pair in the n by n matrix, then we find out the transition function of Qi with the A input and the transition function of Qj with A input, and we mark for some input alphabet. After all the unmarked pair, we combine all the unmarked pair Qi Qj and make them a single state in reduced DFA. So we take an example and follow this algorithm step by step. Okay, so the example is, see, this is a DFA. Okay, in this DFA we have more than one final state, that is P, T and R. These three states are final states, and U, Q and S are three non-final states. So this Myhill-Nerode theorem or table filling method is used to minimize the DFA which contain more than one final state. So this theorem can be applicable to this problem. So what is the first step? The first step is that we draw a table of n by n. N is number of states. Okay, n is number of states. So we create n by n matrix or a table Qi Qj for all the pair of Qi Qj, and it is not necessarily that they are connected to each other directly or indirectly, and initially we unmark it all and delete the diagonal upper part. So how we create a table? So the step one is there are four states U, P, Q, R, S, T. So we take n by n. So U, P, T, Q, S, R. Similarly, U, P, T, Q, S and R. Now we create this table like this. Okay, and in the first step itself, we have to delete the diagonal upper part. So we create a dash diagonal line like this, okay, and delete the upper part of this diagonal. So like this means while considering or while solving the algorithm, while solving the question, we do not find any solution for this upper part, and for the half part of the cell like this, this. So this shaded portion we do not find any solution. So we delete the diagonal upper part and the remaining half cell. So we find the solution for this full cell for each pair of these cells. So this is the first step, that we create a n by n matrix and we delete the upper part. Now the second step is we consider every state pair Qi Qj in the DFA where Qi belongs to final state and Qj does not belong to final state and vice versa, and we mark them one by one. So second step is we consider one pair one by one. So for example, we consider this first pair. The first pair is U comma P. So this cell means U comma P. So we find out whether U belongs to the final state. See here, U does not belongs to the final state and P belongs to the final state. See here in the question, U does not belong to the final state and P belongs to a final state, and in the question say that Qi, between the pair of Qi and Qj, one of the state belongs to final and another state belongs to the non-final state, then we mark it properly. So in this case, for the pair of U comma P, U does not belongs to final and P belongs to final, so we mark like this. So now the next pair is this cell. This cell means the pair is known as U comma T. So for U comma T, see here, U does not belongs to final state and T belongs to the final state, so we mark it like this. Now the next cell is U comma Q. For U comma Q, U does not belongs to final state and Q does not belongs to final state, so we leave it as it is by cross. Now the next cell say U comma S. So U does not belong to the final state and S also does not belong to the final state, so we do not mark it, and we do not mark this cell and show it by a cross sign. Now this cell means U comma R. See here, U belongs to the U does not belong to the final state and R belongs to the final state, so we mark it like this. Now the next cell is P comma T. This cell says P comma T, in which P belongs to final state and T belongs to final state. So both states belongs to the final state, so we do not mark it and we show it like by cross sign. Now next this cell contain P comma Q. So P, in which P belongs to the final state and Q does not belong to the final state, so we mark it like this. Now this cell is P comma S. For P comma S, P belongs to the final state, S does not belong to the final state, so we mark it like this. Now this cell is P comma R. In P comma R, P belongs to the final state and R also belongs to the final state, so we do not mark it like this and shown by cross sign. Now for this cell means T comma Q. T belongs to the final state, Q does not belong to the final state, so we mark it like this. Now this cell is T comma S. For T comma S, T belongs to the final state and S does not belong to the final state, so we mark it like this. Now for this cell is T comma R. T belongs to the final state as well as R belongs to the final state, so we do not mark it and shown by cross sign. Now the remaining cell is this. So this cell is Q comma S. Q does not belong to the final state and S also does not belong to the final state, so we do not mark it and shown by cross sign. Now the next cell is Q comma R. Q comma R. Q does not belong to the final state and R belongs to the final state, so we mark it like this and shown by a tick sign. And the last cell is S comma R. See here, S does not belong to the final state and R belongs to the final state, so we mark it like this. So this is the second step in which we consider each pair of this table and find out whether one of the state belongs to the final state and another state does not belong to the final state, so we mark it by a tick sign, and the remaining cell we mark it by a shown by a cross sign. So this is step 2. Now what is the step 3? Repeat this step until we cannot mark any more states and if there is an unmarked pair. So currently we have some cell which is unmarked like this 1, 2, 3, 4, 5, 6. So we have 6 cells which are unmarked. So for that purpose we consider the transition function of Qi comma A, that is A is the input. For in case of our example, the input are A comma B, small a and small b. So we find out the transition function of Qi comma A and Qj comma A and check whether that pair is marked in the table or not. How we find it? So we consider the first cell. So for the step 3, the first unmarked cell is this. This cell is U comma Q. So or you can say first we consider this cell unmarked cell, that is this is P and T. So we consider unmarked cell, that is P comma T, and we find out the transition function of P comma A because our input is small a and small b. So we find out P comma A and transition P comma A. Similarly, transition function of P comma B and transition function of P comma B. Now see here, in case of this example, with P and with small a it gives Q, P small a it gives S, P small b it gives S, and T small b it gives Q. So the pair becomes Q comma S and S comma Q. Now check in the table whether this pair, this resultant pair is marked or unmarked in the cell. So see here Q comma S. Q comma S is unmarked. This is unmarked, and S comma Q, S and Q. So S comma Q does not exist. So we can say it does not exist. So this P comma T remain unmarked. So we consider this step is 1. So for our convenience, this cell becomes 1. So we have to calculate all the transition function and check whether that resulting answer is marked or unmarked for all the unmarked pair. Now we consider the next unmarked cell, that is this, and we consider this cell as 2. This cell is U comma Q. So for second pair U comma Q, we find the transition of U comma A and Q comma A. Similarly U comma B and Q comma B. Now check with the help of an example. U comma A, U with small a gives P, Q small a it gives R, U with small b it gives T, Q with small b is R. So the pair becomes P comma R and T comma R. Now we check that these resulting pair P comma R and T comma R in the table is marked or unmarked. So first pair is P comma R. P and R is unmarked, and T comma R, T and R again it is unmarked. So we leave this U comma Q remain unmarked. Okay. Now we consider the next cell and name it as 3, and this cell is U comma S. So to calculate U comma S, we find out the transition U comma A, S comma A, similarly U comma B and S comma B. So for the given question, U comma A, U with small a is P, and S with small a, it gives R. Now U with small b, it gives T, and S with small b, it gives R. So the pair becomes P comma R and T comma R. Now check the resulting pair P comma R and T comma R in the table. First we check P comma R, it is unmarked, and the next pair is T comma R, it is again unmarked. So these two pair P comma and P comma R is unmarked. So we remain unmarked this pair. Which pair? That is U comma S. That is number 3. Now we check another cell which is unmarked. The next cell is this one and we name it as 4, and this cell becomes P comma R. Now the fourth is P comma R. So for P comma R we check the transition value. So how we calculate it? The transition of P comma A and R comma A, similarly P comma B and R comma B. So to find it, P comma A, check here, P with small a, it gives Q, R comma A, R, for this question, just 1 minute, for this transition value for R and AB, it remain in the same state. So R with A, it gives R. Now P comma B, P with small b, it gives S, and R comma B, it gives R. So the resulting pair is Q comma R and S comma R. Check in the table, Q comma R, Q and R is marked, and S comma R, S and R is again marked. So now we mark this cell and P comma R. P, where is P comma R? P comma R is 4 cell, and so we mark this cell. Now the unmarked pair is again, that is T comma R. Now we make it a 5th pair, T comma R. Now we check the transition value, T comma A and R comma A, T comma B and R comma B. Now calculate the value. T with small a, it gives S, R with small a, it gives R, T with small b, it gives Q, and R with small b, it gives again R. So the resulting pair becomes R comma S and Q comma R. Now check in the table whether this resulting pair is marked or unmarked. S comma R is marked, and Q comma R, Q and R is again marked. So it means that T comma R pair is or can be marked. So the number 5 cell we mark it. Now the last unmarked pair will be Q comma S. Now if we calculate Q comma S, so we get the function Q comma A, S comma A, Q comma B and S comma B. So for the example, Q with small a, it gives R, S with small a, it gives R, Q with small b, R and R. So the resulting pair is R comma R and R comma R. Now check the pair in the table. R comma R does not exist for both the resulting, not exist. This means we remain Q comma S unmarked. So we leave this and mark it the cell. Now again check how many cells are unmarked remain. That is number 1 and 2, 3 and 6. So we again check whether this after all the updation, whether this pair will be marked or not. So for the first cell, that is P comma T. Now for the P comma T, the resulting pair is Q comma S and S comma Q. Now check Q comma S. Q and S is unmarked and S and Q does not exist, so we leave it as it is. So for again checking the first unmarked cell, that is P comma T, remain still unmarked. Okay. Now the next pair is 2. What is 2? U comma Q. The resulting pair is P comma R and T comma R. Check P and R will be marked and T comma R will be marked. This means for the second updation, U comma Q will be marked. No, so this mark it. Now the third set is U comma S. Check the resulting pair is P comma R and T comma R. P and R is marked and T and R is marked. So for the second updation, U comma S will mark. So we mark this. Now the last unmarked pair is number 6, that is Q comma S. So Q comma S, the resulting pair is R comma R and R comma R. So the R comma R does not exist. So we this means that Q comma S still remain unmarked. So this means that P comma T and Q comma S remains the unmarked cell. Now the last step says that we combine all the unmarked pair Qi and Qj and make them a single state in the reduced DFA. This means that now in the current position P comma T and Q comma S will be combined in a same state or in a single state. What are the pairs? P comma T and Q comma S. So P comma T means these two states combined in a single state, and the next pair is Q comma S. This is Q comma S will be combined. So the reduced DFA will be, so the last step is reduced DFA, in which we combine P and T and Q comma S. So the answer is, we have an initial state U, okay, then we have a state P comma T which is not P comma T, it's PT, and this means that the two different state P and T are combined in a single state. Similarly, the next state is QS, and the last state, which is a final state, is also R. But see here, the P and T, these two states are final state. So we mark this PT, which is a new state, as a final state. Now we take the transition value for the basic DFA. So this means that in the given DFA, P comma T and Q comma S remain in a single state, in which P and T are the final state. So we create this P comma T, which is a single state, becomes a final state, and R becomes a final state. Now see here, U is the initial state. U with small a input, it goes to P, and U with small p, it goes to B. So this means that U with small a and B, it goes to PT. Now for P state, with small a with Q, A with Q, and for B it goes to S, so A comma B. Now for T with small a it goes to S, T with small a it goes to S, and T with small b it goes to Q. Now for Q, A and B it goes to R, A and B, and for S, for A and B it goes to R. So this remains the same, and for R, for A and B input, both it remain in the same state. So for the given DFA, and with the help of the Myhill-Nerode theorem or table filling method, the reduced DFA or the resulting DFA look like this, in which we combine the two states, that is P and T and Q and S. So this is how we solve the problem with the help of a Myhill-Nerode theorem, which is used for minimizing the DFA. And if you have any query, then you can ask in our comment section. So keep watching my video. Thank you so much.